Hello everybody, my name's Iman. Welcome back to my YouTube channel. Today we're going to be covering Chapter 6 for our MCAT General Chemistry playlist. Now this chapter is titled Equilibrium, and we're going to cover three main objectives. The first objective is titled Equilibrium. Here we're going to talk about reversible versus irreversible reactions, and we're going to specifically focus on reversible reactions and begin to discuss chemical equilibrium. For that, we're going to need to define, understand, and learn how to calculate the equilibrium constant expression for a reaction. We're also going to discuss how to determine the sign of delta G, change in Gibbs free energy, and the direction of a reaction given the equilibrium constant expression. Now, the second objective is titled Le Chatelier's Principle. This is a French name, so forgive my pronunciation. In this objective, we're going to learn how to use this principle to determine how changing conditions like temperature, pressure, concentration will affect a reaction that's in equilibrium. The last and final objective is titled Kinetic and Thermodynamic Control. So in this final objective, we're going to identify the conditions that will cause a reaction to favor the kinetic or the thermodynamic product. In addition, we're going to cover how to distinguish between a kinetic and a thermodynamic pathway on a reaction coordinate diagram. Now, to begin this chapter, I want to remind you the distinction between kinetics from last chapter and equilibrium. Kinetics and equilibrium are two fundamental concepts in chemical reactions that, while related, describe different aspects of a system. Kinetics is the study of reaction rates, which involves the speed at which a reaction proceeds. It's concerned with the journey of a chemical reaction from reactants to products. Factors that affect the rate of reaction include the concentration of reactants, temperature, and the presence of a catalyst. Now, on the other hand, equilibrium is concerned with the destination of a reaction. It describes the state at which the concentration of reactants and products have become constant due to the fact that the forward and reverse reactions are proceeding at the same rate. And at that point, the system is said to be in equilibrium. With that, we can officially begin this chapter. Now, chemistry fundamentally explores how substances interact and transform into new substances. This transformation involves reactants. These are substances that enter a reaction, turning into products. These are new substances produced by the reaction. Now, most chemical studies really focus on understanding the nature of these transformations, which can vary greatly in their behavior and in their outcomes. Now, chemical reactions can be broadly classified into two categories based on their directionality. One category is irreversible reactions. These reactions proceed in one direction. Once the reactants are converted into products, the reaction stops because the products do not readily convert back into the original reactants. So a good example of this is the combustion of gasoline. It releases energy and gases that do not easily reform back into gasoline. The second category is reversible reactions. So unlike irreversible reactions, reversible reactions do not proceed to completion. The products formed can react among themselves to regenerate the original reactants, and this back and forth can occur indefinitely. Now, we're going to focus on reversible reactions in this lecture. And within the context of reversible reactions, chemical equilibrium represents a state where the rate of the forward reaction equals the rate of the reverse reactions. So the rate of the reactants converting to products equals the rate of the products converting back to reactants. And this balance results in the concentration of both reactants and products remaining constant over time, defining the dynamic nature of chemical equilibria. Now, it's crucial to understand that at equilibrium, the reactions have not ceased. They haven't stopped. They continue to occur in both directions at equal rates. And this dynamic equilibrium is really a key concept in understanding how chemical reactions can be influenced and can be controlled. Now, to quantitatively analyze a chemical equilibrium, we're going to use a crucial tool called the equilibrium constant, denoted as capital K. Now, let's consider this generic chemical reaction right here. We have A moles of reactant A and B moles of reactant B that form C moles of product C and D moles of product D. Now, the balanced chemical equation written right here, the lowercase letters A, B, C, D, they represent the stoichiometric coefficients in this reaction, and they indicate the proportions in which the reactants and products participate in the reaction. Now, the equilibrium constant expression for this reaction is given by the following expression. We have K equals the concentration of products raised to their stoichiometric coefficients and multiplied together. And that's all divided by the concentration of the reactants raised to their stoichiometric coefficients and multiplied together. And so here in this reaction, in this expression, it helps us understand the extent of the reaction at equilibrium. And in short, that equilibrium constant K is just calculated as the ratio of these two products. The product of concentrations of the products over the product of concentration of the reactants, and everything is raised to its stoichiometric coefficient. This formula shows us how the concentration of reactants and products at equilibrium affect the progress and extent of the reaction. Now, the next thing we want to talk about is the law of mass action. This is going to help us understand the foundation for the equilibrium constant expression. Now, the law of mass action states that at equilibrium, the rate of the forward reaction is going to be equal to the rate of the reverse reaction. And this principle actually allows us to write the rate expressions for both the forward and reverse reactions in terms of the concentrations of the reactants and products raised to the power of their stoichiometric coefficients. So allow me to show you what that means. Here is our generic chemical reaction again. Because of the law of mass action, for this generic reaction, we can write the rate of the forward reaction and the rate of the reverse reaction. We have that here. So this is the rate of the forward reaction. Notice that it's equal to Kf and the concentrations of both reactants raised to their stoichiometric coefficients. And here is the rate of the reverse reaction. We have Kr and then the concentrations of the products raised to their stoichiometric coefficients. Now, at equilibrium, the rate of the forward reaction and the reverse reaction are equal. And so that means we can set these two expressions equal to each other. And we get the following expression because of that. Now, what we can do to this is rearrange this equation to give us our equilibrium constant expression. We're going to move our K terms to one side, and then we're going to move all our concentration terms to the other side. And what we get is the following expression, which looks like our equilibrium constant expression. Now, a couple of things here. If you remember last chapter, we said that for rate laws, the exponents are determined experimentally. Why is it here that we wrote the rate laws for the forward and reverse reactions using the coefficients from the balanced reaction? Again, this is a consequence of how we define the law of mass action. Think of it this way. When a chemical reaction reaches equilibrium, the rate at which the reactants turn into products is the same as the rate at which products turn back into reactants. And the equilibrium constant K tells us about this balance. That means it uses these stoichiometric coefficients, those numbers in front of the chemical formulas in the balanced equation, because those coefficients represent the actual proportions of molecules reacting with each other at equilibrium. And so it is okay to write the rate of the forward and reverse reactions at equilibrium in the manner that we did. Now, in addition, the law of mass action provides a bridge between the concepts of kinetics and equilibrium. It allows us to understand the rate at which reactions occur and the proportions of reactants and products present at equilibrium. And a consequence of this is that it allows us to predict the direction a reaction will proceed to reach equilibrium when conditions like concentration, pressure, or temperature change. Now, with all this information, let's go ahead and hop into a practice problem. This problem asks, what is the expression for the equilibrium constant for the following reaction? We have 3 moles of hydrogen gas reacting with 1 mole of nitrogen gas to give us 2 moles of ammonia. Now, before we tackle this problem, there's an important point I want to make here. When studying chemical equilibrium, you might encounter different notations for the equilibrium constant, such as KEQ, the equilibrium constant at equilibrium, or KC. And although they're related, each has its specific context and application. KEQ, this is the general equilibrium constant for any reaction at equilibrium. Kc, this is equilibrium constant specifically in terms of molar concentrations, and it's used for reactions in solution. Therefore, KEQ is a broader term that can be used in any context where an equilibrium constant is relevant. And Kc is specifically used for solutions where concentrations in molarity are measured. Now, in the context of the MCAT and most purposes, for dilute solutions, KEQ equals Kc, and both are calculated in units of concentration. And so for this problem, we can write the equilibrium constant as KEQ or Kc, and that's going to be equal to the concentration of the product, ammonia, raised to its stoichiometric coefficient, over the concentration of the reactants raised to their respective stoichiometric coefficients. So this is what our expression for the equilibrium constant would look like for this reaction. Now, one more thing, you might see Kp. This is the equilibrium constant in terms of partial pressures. It's used for gaseous reactions. So for example, if you were asked to write the Kp for this reaction, it would look very similar to Kc, except it will not be in concentrations, it will be in pressures. So you would write the pressure of the products raised to their respective stoichiometric coefficients over the pressure of the reactants raised to their respective stoichiometric coefficients. So very similar. Wonderful. Now that we've solved this problem, the next thing that we want to learn is how to do equilibrium calculations. And this is a topic that's best taught using a guided example. So let's go ahead and read this problem. The problem asks, what are the concentrations of a 0.15 molar solution of hydrogen cyanide? We're given the balanced chemical equation, and we're also given the equilibrium constant. So what's our game plan? Well, with this information, we want to initially write up our expression for the equilibrium constant. We aren't trying to calculate K here. We're given that value. Instead, we want to set this expression up and work backwards from there to accomplish our actual goal, which is figuring out the equilibrium concentrations of these species in this reaction. But notice that we can't plug in values into that kind of expression just yet because we know what we're starting off with in terms of reactants and products, but not the actual equilibrium values. And you need the actual equilibrium values to calculate and use the equilibrium constant expression. So then, in order to do that, we're going to have to set up and use a strategy called the ICE table or reaction table. ICE here is an acronym standing for Initial, Change, and Equilibrium. So how do we use this ICE table, and what is this ICE table? The ICE table is an organized way to approach problems involving equilibrium. It allows us to track the concentrations of reactants and products at 3 different stages: the initial concentration, the change that occurs as the system reaches equilibrium, and finally, the equilibrium concentrations. So let's go ahead and set this up for our problem. Starting off with initial concentrations, we're given that we're dealing with a 0.15 molar solution of hydrogen cyanide. So that is our concentration for hydrogen cyanide. This is the beginning of the reaction, so no products have formed just yet. That means the concentrations of the hydrogen and cyanide ions is just 0. The next category is the change category. We can represent the change in concentration with the variable X. So here we're consuming the reactant, hydrogen cyanide, to form product, hydrogen and cyanide ions, until we reach equilibrium. So if we're consuming hydrogen cyanide, we're gonna set that as minus X because we're consuming the reactant. And then we're gonna set the products as plus X since we are forming them in this reaction. Now, please note that this variable X is going to have a coefficient that's similar to the coefficient used in the reaction, in the balanced reaction. So here, these are all just 1, but if the reaction had 2 for the hydrogen ions, you would want to accommodate for that because we're using this change and we want it to be balanced with the ratio of moles in the balanced chemical equation. All right, so that's our change, minus X for hydrogen cyanide plus X for the hydrogen and cyanide ions. Then our final category is the equilibrium. The final row here is going to be the initial concentration minus or plus the change. So for hydrogen cyanide, that's going to be 0.15 minus X. And for hydrogen and cyanide ions, that's just going to be plus X. Now here, what we're going to do next is set up our equilibrium constant expression. We know that our equilibrium constant is equal to the concentration of the products raised to their stoichiometric coefficients over the concentration of the reactants raised to their stoichiometric coefficients. And that equals K, which we are given. That's 4.9 times 10 to the minus 10 power. Now, we can begin to replace these terms with our equilibrium terms that we've determined from our ICE table. So the concentrations of hydrogen and cyanide ions can be replaced with X's, and then our concentration for hydrogen cyanide can be replaced with 0.15 minus X. Now, this is actually a very complicated calculation to do, especially if you do not have a calculator. And we all know in the MCAT, we don't have calculators. Now, in many equilibrium problems, we can actually simplify our calculations by making the assumption that the change in concentration of a reactant or product is negligible compared to the initial concentration. This rule is usually known as the 5% approximation rule, and it's a guideline that helps determine what is a reasonable assumption to make. What is a reasonable simplification assumption? The rule essentially states that if the change in concentration X is less than 5% of the initial concentration, then X is negligible. And this is often valid when K is very small or very large, and when the initial concentration is significantly high. This assumption will be a safe bet for the MCAT, because without this assumption, solving this problem will be very complicated because you're going to need to use the quadratic formula, and that is outside the scope of the exam. What that means then, when we use this 5% approximation rule is that this denominator, the 0.15 minus x term, just becomes 0.15. So this is what we have to work with, and this is going to be a lot easier to calculate. Now again, conceptually, know this conceptually, it's going to be important to know when to make this assumption and when not to make this assumption. While in the calculation portion, you can always make this assumption, you might be asked a conceptual question about when it is appropriate to use this 5% approximation rule. And so the case for that is in cases where K is of comparable magnitude to the initial concentration, or when we don't have a huge excess of reactants, you cannot use this assumption. But when K is very small or very large, which is the case here, look at K, it's very small, you can make this assumption. So in our problem, we indeed can make this assumption. And what we have to work with now is the following. Now we have x squared over 0.15 equals 4.9 times 10 to the minus 10. And this is a simple calculation to make to solve for x. Now that we've explored these concepts for equilibrium calculations and some of the important assumptions we can make and the important tools we can use like ICE table, let's jump into another practice problem. This problem states 3 moles of dinitrogen tetroxide is placed in a 0.5 liter container and allowed to reach equilibrium according to the following reaction. What is the equilibrium concentration of nitrogen dioxide given that the equilibrium constant for the reaction is 6 times 10 to the minus 6? Wonderful. The first thing that we're going to do is set up our equilibrium constant expression with the given information. So we know that K is equal to 6 times 10 to the minus 6. And our equilibrium constant expression is the concentration of your product, which is nitrogen dioxide here, raised to its stoichiometric coefficient, over the concentration of your reactant, raised to its stoichiometric coefficient. Now, what we want to figure out next is our equilibrium concentration, so we can begin to plug in stuff here and solve the equilibrium concentration of nitrogen dioxide. This is going to require us to set up an ICE table. So that's exactly what we're going to do here. We're going to set up our ICE table. We have dinitrogen tetroxide, and that gives us, 1 mole of that gives us 2 moles of nitrogen dioxide when it reacts. And we're trying to figure out the initial, the change, and the equilibrium. So we are given information to figure out our initial concentration of our reactant dinitrogen tetroxide. We're not given the concentration explicitly, but we're given just enough information to calculate it ourselves. We're given the number of moles of dinitrogen tetroxide, and we're given the volume of the container. And so to figure out the concentration of this reactant, we're just going to take the moles and divide it by the volume, because moles over volume equals concentration. 3 moles over 0.5 liter gives us a 6 molar concentration for dinitrogen tetroxide. Wonderful. So that's our initial concentration for the reactant, and our initial concentration for the product is 0. Now, what is going to be the change here? Well, we're going to be consuming the reactant to form product. So we're going to assign the change for our reactant as minus 1x, because we're going to consume reactant, and we're going to form product. So we're going to say that the product is plus 2x. We get that 2 from the stoichiometric coefficient. We want to make sure that the coefficients associated with this X change matches up the mole-to-mole ratio of reactant and product here. So we're going to consume minus X of the reactant to form plus 2X of the product. Now our equilibrium is just going to be our initial minus or plus the change. So our equilibrium concentration for our reactant is going to be 6 minus X, and for our product is just going to be 2X. Now we can go ahead and plug these values in to our equilibrium constant expression. Now we can write that 6 times 10 to the minus 6 is equal to our product concentration, which is 2X squared raised to that stoichiometric coefficient over our equilibrium concentration for dinitrogen tetroxide, which is 6 minus X. All right, wonderful. Now here's where we can make an assumption. We can use our 5% approximation rule, and we can do this confidently because look at our value for K. It's very small. And so that means that our 5% approximation rule is probably valid to use. And what that does for us is simplify our calculations because now we can approximate this 6 minus X term to just 6. All right, so now our denominator is just 6 instead of 6 minus X. And this makes our math very easy. Now we can multiply both sides by 6. That gets us 36 times 10 to the minus 6 equal to 2x squared. Let's expand this right here. That squared goes to both terms inside the parentheses. So what we get actually is 4x squared. Now we can divide both sides by 4. When we do that, we get 9 times 10 to the minus 6 is equal to x squared. And now we can take the square root of both sides. This gives us that x is equal to the square root of 9 times 10 to the minus 6. This is going to be easy if you just remember that this is like doing the square root of two different terms. What's the square root of 9? That's 3. And what's the square root of 10 to the minus 6? That's also easy. That's just like dividing that minus 6 by 2. That's equal to 10 to the minus 3. Now, please don't make the mistake of thinking that this is our answer. This is just what X is. And our goal is to figure out the equilibrium concentration of nitrogen dioxide. Now that we know X, we can plug it back into our equilibrium term for nitrogen dioxide. And our equilibrium term for nitrogen dioxide is 2x. So we're going to have to multiply x by 2 to get our final answer for the equilibrium concentration of nitrogen dioxide. Now, 2 multiplied by 3 times 10 to the minus 3 is just 6 times 10 to the minus 3. That is our equilibrium concentration of nitrogen dioxide. And with that, we have solved the problem. Wonderful. Now with that, we want to transition into a different topic. And this topic revolves around the law of mass action again. We said that the law of mass action defines the position of equilibrium. But achieving equilibrium takes time. And it can vary from microseconds to millennia, depending on the rates of the forward and reverse reactions. Keeping that in mind, then, it's important to be able to gauge how far a reaction has progressed towards equilibrium. And the way that we do that is we use the reaction quotient Q. At any point during a reaction, we can measure the concentrations of all reactants and products and calculate Q using the following equation. Now, this equation looks identical to the equation for the equilibrium constant, but the information it provides is different. While the equilibrium constant is calculated only at equilibrium, Q, the reaction quotient, can be calculated at any time. The concentrations used to calculate Q change over time as the reaction proceeds. So Q provides a snapshot of where the reaction is at a specific point in time, whereas the equilibrium constant K describes the end state of the reaction. Now, comparing Q to K actually allows us to predict which direction the reaction will proceed to reach equilibrium. When Q is less than K, then the forward reaction has not yet reached equilibrium. The reaction is going to proceed forward to reach equilibrium, converting more reactants to products. When Q equals K, the reaction is in dynamic equilibrium. And so the reactants and products are present in equilibrium proportions, and the forward and reverse rates of the reaction are equal. When Q is greater than K, then the forward reaction has exceeded equilibrium. The reaction will now proceed in the reverse direction to reach equilibrium, converting more products back to reactants. Now, in addition to this information, comparing Q and K and what that means for if the reaction is moving forward or reverse, we can also extract information about the Gibbs free energy. So it's really important for us to understand how these concepts relate to Gibbs free energy and the direction of chemical reactions. Now, when Q is less than K, what does that mean for our Gibbs free energy? This means that the change in Gibbs free energy is negative, indicating that the forward reaction is spontaneous. The reaction will proceed in the forward direction to convert reactants into products until equilibrium is reached. Now, when Q equals K, what does that mean for our Gibbs free energy? That means our Gibbs free energy, our change in Gibbs free energy is going to be equal to 0. Now, this indicates a state of dynamic equilibrium where the forward and reverse reaction rates are equal. That means there's no net change in the concentration of reactants and products. And then last, when Q is greater than K, delta G is going to be greater than 0. This indicates that the forward reaction is non-spontaneous. The reaction will proceed actually in the reverse direction to convert products back into reactants until equilibrium is reached. And we can see this relationship demonstrated in the figure here, where we have Gibbs energy versus reaction quotient. We can see that when Q equals K, delta G equals 0, and the reaction is at equilibrium. But when our relationship between Q and K changes, so does our delta G. Now, some final points to consider before we move into our next objective are the following. Now, the first point deals with the exclusion of pure solids and liquids. The concentrations of pure solids and pure liquids do not appear in the equilibrium constant expression because their activities are defined as 1. So if you see a reaction where something is a liquid, all right, something is a liquid, that is not included in our equilibrium constant expression. Make sure to omit that when you are writing the equilibrium constant expression. Solid liquids, not included. The second point has to do with temperature dependence. The equilibrium constant K is characteristic of a particular reaction at a given temperature. Please note that changing the temperature will change the value of K. The third point deals with the magnitude of K. The larger the value of K, the further to the right the equilibrium position lies, indicating a greater concentration of products relative to reactants. On the other hand, a smaller K value indicates an equilibrium position that favors the reactants. And the last and final point to keep in mind is the direction of the reaction. If the equilibrium constant for the forward reaction is K, then the equilibrium constant for the reverse reaction is 1 over K. These are all important points regarding our equilibrium constant that we should keep in mind. And with that, we have actually completed our first objective for chapter 6. We're going to end the video here. In the next video, we're going to cover our next 2 objectives. I hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.